As you've seen in many of your math classes up until this point, solving equations is a really important thing that we do in mathematics. In algebra, we learn how to solve linear and quadratic equations, and in pre-calculus, we learn how to solve rational, exponential, logarithmic, and trigonometric equations. Oftentimes up to this point, these have been kind of nice equations that have been able to be solved, using functions that we're familiar with. That won't always be the case though, and today we're going to look at equations that cannot be solved quite as easily, and we will look at a method called Newton's method that can be used to approximate solutions to those kinds of equations. Let's start with a nice equation first, something maybe you're familiar with. Say we want to solve the equation x cubed minus x squared equals 0. Okay, so first thing we'd do if we were solving an equation like this, we would go ahead and factor the x squared out, and we'd be left with x minus 1 in the parentheses there. And then these two things multiply to give 0, so that means one of them has to be 0, right? So either x squared equals 0 or x minus 1 equals 0. And x squared is 0 when x is 0, x minus 1 is 0 when x is 1. That should look relatively familiar. So there are two solutions to this equation, and sometimes when we look at solutions to an equation, we can put it in set notation if we want to. So the solutions to this equation would be 0 and 1. So that's an example of a nice equation that you may have seen before. But we are somewhat limited on what kinds of equations we can solve analytically, like we just did. For example, if we just change this equation ever so slightly to x cubed minus x squared minus 1 equals 0, this equation can no longer be solved by algebraic means. Or similarly, if we wanted to solve the equation cosine of x equals x, so then we're kind of mixing some different types of functions together, that also cannot be solved algebraically. But there are methods that we can use to approximate solutions to those types of equations, and believe it or not, we can actually usually use these methods to get as accurate results as we want to, with actually relatively minimal effort. You might be surprised. So the technique we're going to focus on today is called Newton's method, and it's built around using tangent lines. The idea is that if we kind of know roughly where a 0 is, or kind of have an idea of something close by, what we can do is we can pick some number x to be close to a 0 of f, so that is where a function might cross the x-axis. Pick some x-coordinate close by, maybe a nice whole number or something like that. Then you can take the tangent line to that function at that point, and if you picked well enough to begin with, and you'll see some different examples later on, then what should happen is that the tangent line should cross the x-axis at a point even closer to the 0 than the original x was. And this method basically takes advantage of the fact that it's relatively easy to solve linear equations. So this is what Newton's method looks like geometrically. This isn't really going to be how we actually perform Newton's method. We're going to later come up with a more algebraic process for approximating the 0 of a function. But here's the main idea. I'm going to kind of zoom in on this a little bit. So here's some function here you see in blue, some curve. And the idea is that you begin with an initial guess, roughly where the 0 is, and we call this x sub 1. Now, I took this figure from an online textbook called Apex Calculus. They happen to choose x sub 0 instead of x sub 1 as being the first starting point, and you'll see variations in this. But to make this kind of match what I have here, I'm going to go ahead and just call this here x sub 1, and feel free to do that in your notes as well. You can just scribble out that x sub 0 and name it x sub 1 instead. So the idea is this is the actual 0 that I'm looking for, this x coordinate here. That's what we're trying to find, is the 0 of the function. So we pick some convenient x coordinate nearby. Maybe this is a whole number or something like that. We go up to the curve and we draw a tangent line. And we look for where that tangent line crosses the x-axis. And we call that the next iteration, basically. That would then be x sub 2. And then what we do is we take this new x-coordinate and we do the same thing again. This is an iterative process where we kind of just continue to repeat that same thing over and over again, and it'll eventually kind of narrow in onto that 0 that we're looking for. So we pick x2 next, right? We draw a tangent line, and then we get some other x value that's even closer to the 0 that we were looking for to begin with, right? So notice x sub 1 is a certain distance from this 0, and x sub 2 is even closer, x sub 3 is even closer. We're going to repeat the process again. We take that x sub 3. Sorry, let me just fix these real quick. X sub 1, that was x sub 2. This was x sub 3. Now we plug x sub 3 in, and we find the tangent line there. And notice how close this one is. Like, you can barely even see it, see the difference between the two, but there certainly is. It's right there is the 0 of that tangent line. And so that would be x sub 4. And you can continue to repeat this process over and over again until you get as close as you want to that particular 0 of the function. My arrow is bothering me because it looks kind of like a 5. Right there, that's x sub 4. There we go. So you can continue to do this. As you can see, geometrically, it's probably not the best process when you're just kind of eyeballing things. But if we look, we can kind of take this geometric process and turn it into a more algebraic process. So we're going to do some algebra now, as you can kind of see. So we're going to begin with an initial guess, again, roughly where the 0 is. We will call that x sub 1. Okay, and I'm going to kind of zoom up just a little bit just so I can, or scroll up rather, just so we can kind of visualize this, okay, and what we're actually going to be doing. So the idea is we've got some initial guess, right, some x value, and we want to find the equation of the tangent line to the function at that particular point. Well, we've gotten pretty good at finding equations of tangent lines. So we know that the equation of a tangent line is y equals the derivative at a point, x minus a times, so f prime of a times the quantity x minus a plus f of a. Now we are wanting to use x sub 1 instead here for our a value, basically. So we'd have y equals f prime of x sub 1, x minus x sub 1, plus f of x sub 1. And we will call this L sub 1 of x. So I'm going to get rid of my y and just call that L sub 1 of x. So this is the linearization of the function at that point. This would be the equation of the tangent line at x sub 1. Okay? Now what we're going to do is we're going to use that equation of the tangent line, and we're going to find the x-intercept of that line. Okay, so I'm going to scroll up here again. So we have found the equation, this piece here, we have found the equation of that black line. What we want to do now is find the x-intercept of that tangent line. So we know to find an x-intercept, that is where it crosses the x-axis. That is where the y-coordinate is 0, right? So we want to set this equal to 0 and then solve for x. So we will set that y value equal to 0. And we are going to try to solve for x. Just as a reminder here, this is some number. This represents the slope of the tangent line at that point. So the slope of that line, right? This is a number. It's the x-coordinate, right, where we put the tangent line. This is the y-coordinate where we put the tangent line. So x is the only variable in this equation here. Everything else is a constant. We're just kind of representing those constants in a general way. So we want to solve for x. So we will go ahead and subtract f of x1 to the other side. And then we see on the right side I have this multiplication. So we will go ahead and divide both sides by that f prime of x sub 1. So I get negative f of x sub 1 divided by f prime of x sub 1 equals x minus x sub 1. And we get, I ran out of space, so I'll come over here. Now we'll solve for x by adding x sub 1 to the other side. So I get x sub 1 plus, oops, sorry, not plus, adding that to the other side, minus f of x sub 1 divided by f prime of x sub 1. So what we just found algebraically is the x-coordinate where that tangent line crosses the x-axis. So we have just found this coordinate point here. And we called that x sub 2, didn't we? So we can say then that x sub 2 is x sub 1 minus f of x sub 1 divided by f prime of x sub 1. we're going to repeat that process again. I know it's going to feel a little bit tedious at first, but don't worry, we'll get to a general equation that we'll just be able to remember and use. But this is kind of all leading up to that. So we're going to repeat that process, and we're now going to find x sub 3, which is the x-intercept of basically the next tangent line that we're going to use. This is going to be the linearization of f at x sub 2. Okay, so here we go. We're going to use that same idea. The linearization at x sub 2 would be f prime of x sub 2 times x minus x sub 2 plus f of x sub 2. Okay, and we want to find the x-intercept of this. So we will again set it equal to 0. And we're not really going to go through this whole algebraic process again because we kind of already did, didn't we? We're going to be able to kind of see where this is going to go. Oops. That's what happens when I try to write and talk at the same time. So I'll just put kind of a dot, dot, dot here. We see where this is going, right? And we can see that if I solve this for x, I will have x equals x sub 2 minus f of x sub 2 divided by f prime of x sub 2. And that is our third approximation. So it would be x sub 3 is x sub 2 minus f of x sub 2 divided by f prime of x sub 2. So you can kind of see where this is going. By knowing x sub 1, I can find x sub 2. By knowing x sub 2, I can find x sub 3. By knowing x sub 3, I could find x sub 4. Let me actually put that here. X sub 4, we can see, would be x sub 3 minus f of x sub 3 over f prime of x sub 3, right? So if I know x sub n, I can find the next approximation, x sub n plus 1. X sub n plus 1 is going to be x sub n minus f of x sub n divided by f prime of x sub n. So let's summarize this process and then do an example. So for Newton's method, first the function needs to be differentiable on the interval, basically that has a 0 in it. And to approximate the value of the 0, accurate to however many decimal places we want, d decimal places, we start by choosing a value x sub 1 as an initial approximation of the 0. And a lot of times we'll use a graph to help with this, to kind of get an idea of roughly where the 0 is. And then we'll just kind of continue to, perform Newton's method here until we get to a certain level of accuracy that we're looking for. So basically, once the decimal approximations stop varying to the degree that you're looking for. So for example, if you're trying to find accurate to 6 decimal places, and the 6th decimal place continues to stay the same with successive iterations, then you've gotten the accuracy that you're looking for. So before we do an example, let's take a quick look at this GeoGebra applet for a dynamic visual of Newton's method. And feel free to play with this on your own as well. You can just click the link from the lecture notes. And this is just a random example that happened to be in this applet already. So x cubed minus 4x plus 1. So you can see we have 3 zeros, 3 roots to this particular function. And let's say we're trying to find this largest one, this one over here. It looks like maybe 2 might be a good, if I were just to choose, I probably would have 2 as my beginning point. But just to show you, like I can put this at 3, for example, roughly. And then this is just kind of a visual for it. So we're not going to use this to calculate anything, but just kind of as something to play around with and have a visual for Newton's method. So we start with that x sub 1, and we go to the curve. We draw a tangent line. I think I'll use my arrow instead. Draw a tangent line, and then that x coordinate is what we use for the next iteration. I go up to the curve then, and then draw another tangent line, and then see where that one crosses the x-axis. There it is. And we just continue to do that. So then up to the curve, draw a tangent line. There's the x-intercept of the tangent line, which is very close to the x-intercept of the function. We just continue that process over and over and over again. And you can see as I continue my steps here, our eyes don't even distinguish the differences in what's happening. But if you zoom in and zoom in and zoom in, which I have a touch screen, so I'm just kind of, doing the pinching technique here, you can kind of see there are variations as you continue to zoom. The tangent line, the green tangent line and the blue curve are certainly different from each other, but you can kind of see that they, especially with successive iterations, we get pretty close to the 0 that we are looking for. So again, this is just more of a visual, something that, helps you kind of understand what Newton's method is doing. And now let's go ahead and take a look at an example. So let's take a look at that same equation that we were talking about before, x cubed minus x squared minus 1 equals 0. So there are going to be different variations on instructions here. Sometimes you'll be told what to start with. Other times you won't be told what to start with. So we're going to start with this one where you are told what to start with. Let's say starting with x sub 1 equals 1, find the first 3 approximations. Actually, this should say the third. Find the third approximation. I think I'll try to fix that in your lecture notes so you don't have that. Find the third approximation, x sub 3, to the root of the equation. Okay, now let's actually just take a quick visual of what it is that we're looking for here. X cubed minus x squared minus 1 equals 0. So I'm going to go to, let's just do Desmos, for example, and let's look at that function, x cubed minus x squared minus 1. So we can see that it appears to cross, maybe like 1.5-ish. I can even click here in Desmos and it says 1.466, okay? So it is kind of giving it to us a little bit. But I might want to get more decimal places than that, not just 3 decimal places. It's kind of limited. And it's also nice to see kind of where this number comes from, right? So Desmos is actually using a version of Newton's method to give us this value for that particular x-intercept. So it's kind of cool to see. Think of it as like we're getting a glimpse behind the scenes when we are looking at Newton's method here. So 1 seems like a pretty good starting point. 2 also would be relatively reasonable. So 1 is what we're going to start out with for our first approximation with Newton's method. So let's find the third. Okay, so what we're going to do is we're going to use that process that we just found. Okay, so we have x sub 1 equals 1. Right, we started with that. Now we know x2 is x1 minus f of x1 divided by f prime of x1. Now you might be looking at this formula and thinking, oh, we've got to do all these calculations, and sure, you could go through this process by hand, but you really don't need to. Desmos, and we're going to use GeoGebra as well, can do these derivatives without us having to actually like find the derivative of this function here. I should actually start by saying what we're really doing is solving. We have our function f of x equals x cubed minus x squared minus 1, and we're essentially trying to solve f of x equals 0. So I'll define that function f of x there. So what we're going to do is I'm going to show you 2 different ways to do this, okay? One is going to be in Desmos and one is going to be in GeoGebra. And I'll just let you know from right now, I think that GeoGebra is the way to go with Newton's method. And I'll show you why as we get there. But I know some of us are more comfortable with Desmos. And I know for me at least, like I explored it in Desmos first just because Desmos is kind of my first go-to. But GeoGebra tends to be quite a bit more powerful than Desmos, but I'll show you how to do both, and then you can kind of choose which one you like. So we start with an initial guess. X sub 1 equals 1. That's our initial guess. And this is going to be on a slider, which is actually kind of cool because we can play around with this a little bit and adjust our initial guess and kind of see how it might affect how quickly we get to that accurate root that we're looking for. So then what we can do is just type in x sub 2. Now I'm not typing in a subscript, although you can, but all I am typing is x2 on my keyboard, and it automatically makes it a subscript for me. So you don't have to do any fancy subscripts or anything. But anytime if it doesn't do that, you can always go to this keyboard and do, I think it's under functions and probably miscellaneous. No, it's somewhere in here. See, that's why I like that I don't have to do this. There we go. So it's just in the ABC part. There it is. A sub B. But again, you don't really need to do that. I just wanted to show you just in case it's not coming up. So I can say x sub 2 equals x sub 1. And now because we have told Desmos what x sub 1 is, and we have more importantly told Desmos what the f function is, I can type minus f of x sub 1 divided by f prime of x sub 1. And it's calculating the function at 1, and it's calculating the derivative at 1 within this whole kind of equation here. So it says x sub 2 is equal to 2. So what we've really found here, if you want to visualize it, is we've found the equation of the tangent line, right? There's the tangent line. And notice that the tangent line crosses the x-axis at 2, which is why our second approximation here is, in fact, 2. So now what we're going to do is go up here and find the equation of the tangent line at 2. I mean, we really don't have to find the whole equation. We can just use this formula, can't we? So x sub 3 is x sub 2 minus f of x sub 2 divided by f prime of x sub 2. And I get that the third approximation is 1.625. Now I just want to show you another way we could have done this without having to type it in completely again, is you can copy this. So I just did Control C, but you can also right click. Maybe sometimes Desmos, no, Desmos doesn't really like right clicks. So probably better off, I think you can do it in here. No, never mind. So just do Control C, Control V, that's the way to go. And you can just change this. So I can say x sub 3, x sub 2, x sub 2, x sub 2. So you can tweak it like that. That works also. Notice you get the same thing there. Okay, so I get that x sub 3 is about 1.625. And for a visual, what we just found is the derivative, right, the equation of the tangent line at x sub 2. I'm not sure why I typed 1 in here. I'll just do x sub 1 so that it's more consistent. There we go. And so notice that this crosses at 1.625. So if I were to repeat the process again, I would make, find the tangent line at 1.625, find its x-intercept, and then kind of continue to do that. You can see how much closer that gets. If it doesn't say in the problem to do this, but if I want to see how much more accurate this is. Okay, I know I get 1.4857, etc., for x sub 4. We didn't really need to do that, but. So that's one way we can do Newton's method. And I'll just jot down what we found. We found that x sub 2 was 2 and that x sub 3 was 1.625. Okay, that was using Desmos. Let me show you how we could do this using GeoGebra instead. And again, that's my preferred technique. Now, when you come to GeoGebra, I'll just show you, if you go to justgeogebra.org, you'll see lots of different, tools. The one I recommend is GeoGebra Classic, this one here. So that's where I'm at with this one. And I'll go ahead and close that now as well. Okay, so the way that we want to do Classic, now let me show you something actually. Let me refresh this, because when you first log in, it kind of shows this menu here, and you can click on Spreadsheet, and that will kind of pull up this spreadsheet here. If you happened to miss that, let me just show you. If you don't click on it right away, and like I did, right, I kind of clicked out of it. Oh, it's gone now. You just come up here to the menu and go to Perspectives, and then click on Spreadsheet. Now I still want to see the algebra window because I want to be able to define functions and things like that. So if you just come back up here to the menu and you go to View, you can click on the algebra window again so that you can still continue to input functions and things like that. So when you're doing Newton's method in GeoGebra, I recommend that you have the algebra window, the spreadsheet, and basically like the 2D graphing system here. So you should have basically 3 windows that you're seeing. While I'm in here in this kind of menu, I'm going to also go to settings because GeoGebra's default rounding is 2 decimal places, which just is not enough if you ask me. So I'm going to select 10 decimal places. And you can kind of choose what works for you depending on homework problems, things like that, whether it says to go to 6 or 8 or whatever it might be. Okay, so here we are. Now what we're going to do is we're going to type in that function, f of x equals x cubed minus x squared minus 1. Oops, I typed in x cubed minus x cubed. It's like, that doesn't look right. There we go, that looks better. And then we'll kind of zoom in a little bit. So again, you can kind of see it looks like it crosses a little before 1.5. So we'll make an initial guess about what we think, not necessarily what we think the 0 is, but what a good starting point is for Newton's method. So again, it usually is a whole number that we start with. Let's start with 1 again, just since we are told to start with 1, but that's a pretty reasonable choice anyway. So here's how, there's so many different ways to do this, but here's how I like to do it. I like to keep these, rows kind of in the sequence that I'm trying to do here. So this is going to be my first approximation, the one that generally is chosen. In this case, we're being told it's 1. then this second row is going to be the second approximation, then the third approximation, etc. And what we're going to do is we're going to reference cells within this spreadsheet here, right? Because that's really what we're doing when we do this technique, is we are referencing previous results to get the next result. That's called an iteration. So what we do is we hit the equal sign, equals, and we are going to reference the previous cell. So I want to reference x sub 1 minus f of, click here again, x sub 1 divided by f prime of x sub 1. And I realize you can't see it very well. I wish that you could see a bit more within this spreadsheet, but just do your best with what you have here. Continuing to type will kind of make it show up, right? So you notice when I didn't have that parentheses, I couldn't see it, but once I put it in there, I could see it. And then hit enter. And now here we have the second iteration. We've got, right, x equals 2. So x sub 2 equals 2. Now here's where the beautiful thing comes in. This little kind of square down here allows me to drag this as far as I want to. And there's zero work for me, so I might as well just drag it really far, right? Why not? That's like zero effort. And so what we have is this beautiful spreadsheet that tells us all of these different approximations using this Newton's method. So this is the third approximation, that 1.625 that we found. Now with part A, we're told to stop there. But notice again, minimal effort. We can just keep going with it. Here's the fourth and the fifth and the sixth, and you can kind of see it stops changing after a while, or at least with the 10 decimal places it stops changing. Right when we get to this, right when we get to that seventh approximation, I'm not sure what happened there. There we go. This spreadsheet can be a little bit finicky, I've noticed too. But I do think it works better than Excel or like Google Sheets because we can reference this function here, which is really handy. If you have another way to do this, if you have seen, like if Excel works well for you or Google Sheets, definitely feel free to do Newton's method however you see fit. I really like using GeoGebra because I get to see the graph and then define the function, and it works pretty well. So you can see that after the seventh iteration, we get basically the same 10 decimal places each time. But if we go over here, and if I were to extend the rounding even more, let's say to 15 decimal places, now you'll start to see some variations. They're not really exactly the same. Actually, they are, aren't they? Even to 15 decimal places, they're the same. Let's try going out more. I don't think I can actually go out any more than that. So, yeah. So that's just kind of shows you the accuracy of this Newton's method. You really don't have to do it very many times to get a pretty accurate approximation for that root. Now you might be wondering, how do we document this work on a quiz or on an exam or homework or that kind of thing? And you have several options. You could certainly just write this out by hand. X sub 1 was 1, x sub 2 is 2, x sub 3 is 1.625, etc. But if you do want to give the reader kind of a bigger picture of what you did to get there, you could certainly just screenshot this whole thing and drop it into whatever it is you're doing. So for example, I don't know if the graph is really necessary in this particular case, but I have GreenShot downloaded. It's just a free kind of screenshot software. So if you don't have something like that already, I would recommend that. And you can kind of just snag whichever things you want. I'm going to go ahead and do this because this was the answer to the first part. And then I'm just going to copy it. You could also do save as. And then within my Drawboard PDF app here, I can actually just paste it right in here. Now, I know we all have different technology capabilities, so you do what works for you. But if you were trying to kind of find an easy way where you, I guess, a bit more not having to write so much by hand, this can be a good way to share your work with your instructor or your classmates. So let's take a look at the next part, part B. And we're going to again start with x sub 1 equals 1. We want to find the root of the equation accurate to 8 decimal places and think about how many approximations of Newton's method we ended up having to do for that particular one. So we kind of did this a little bit already, didn't we? I'm going to go ahead and screenshot this. Well, let me get my answer first. so accurate to 8 decimal places. So notice I'm at 1.46557, and it doesn't change anymore after that. So right now we have accuracy to 5 decimal places, actually to 6 decimal places because the ones match here. It is not accurate to 7 decimal places at the 6th approximation. So the 7th approximation, notice the 8th approximation does not change from the 7th approximation. Since those are the same in all resulting ones, we really don't need all of these other ones, but all the 7th and the 8th approximations are the same up to 10 decimal places, then the 7th approximation is accurate to 8 decimal places. Really, it's 10 decimal places, but so I'm going to go ahead and I'll just keep that part highlighted, I think, in my screenshot. And actually, another thing you can do is if you want to minimize the amount of horizontal space it takes up, I can kind of bring that part in a little bit. And I'll show the 8th as well, just so it shows. Feel free to even go to the 9th if you want to. Usually no issue with more information, right? I'll paste that in here. Okay, so this is x sub 7. And notice that that is accurate to 8 decimal places. So the 7th approximation was needed in order to get that level of accuracy. Let's say that we started with a different starting value, maybe 1.5, or maybe we could have even started at 2, right? Because 2 is also relatively close. Notice that when we started with x sub 1 equals 1, x sub 2 ended up being 2. So if we had started with x sub 1 equals 2, we would have had one less iteration needed to get that level of accuracy that we were looking for. But let's say we went even closer and we did 1.5 instead. So 1.5 is our initial, oops, not that one, sorry. Sorry if that happens to you sometimes. 1.5, and then you can kind of see how much sooner we get to that level of accuracy for the 0 of the function. So you can see we actually end up getting there at the 4th approximation if we happen to start our process at 1.5 instead of at just 1. So I'm going to highlight that and screenshot that piece. If you're curious, the app that I'm using is called Drawboard PDF. I believe you have to pay money for it, but it's just an initial amount, or at least it is right now. And it is worth every penny if you ask me. It is really a nice way to just organize everything. So, okay, so we really only needed a 4th approximation to get accurate to 8 decimal places or even 10 decimal places if we started at 1.5 instead. I'll show you how that could have been done in Desmos as well. So if I had just simply done 1.5 instead here, you can also kind of see it's 1.46, all that, yeah. It is a little bit more cumbersome though to compare, I think. So I really do think the GeoGebra spreadsheet is a really nice way to go with these particular problems. All right, let's take a look at another example. This one's going to be a little different than the one that we just did. It says find, correct to 6 decimal places, the root of the equation cosine x equals x. So in the previous example, we had some function. We were basically trying to find when that function was equal to 0, right? Newton's method is really all about helping find x-intercepts using tangent lines. So in this case, we don't really have an x-intercept, do we? We're trying to solve the equation cosine of x equals x. To be able to do that using Newton's method, we want to set this equation equal to 0. So really your first step with Newton's method is just to always make sure that you have something equals 0, and then that something is the function that you're going to be using Newton's method on. So we're trying to solve cosine x equals x. So again, our first step would be to do cosine x minus x equals 0. So let's let f of x equal cosine x minus x. You really should define this function in your work if it's not already done so. Don't assume that your reader knows what f is whenever you refer to f. So make sure that you explicitly define what that particular function is. Now notice we're pretty limited on instructions here, aren't we? But we do want to find it accurate to 6 decimal places, and we're going to use Newton's method to do so. So let's think about how we can go about doing this. I'm going to go up here to GeoGebra. I'm actually going to go ahead and open up a new one, just so that I can have past reference to the other one. And we'll open up Classic. I do have to do some things again, but at least you get to see the process again, right? So if you get in here quickly enough, you can just jump right to Spreadsheet. But I do want to see the algebra window again. View, Algebra. And while I'm here, I will adjust the settings so I have 10 decimal places of rounding. Okay, and now what we're going to do is put in, I'll show you 2 things. Let's start with graphing cosine and then graphing x, because the idea is that we're solving cosine x equals x, right? So when we're solving the equation, what we're really looking for is an intersection point, right? When we're solving when two functions are equal to each other, we're looking for the intersection. It looks like there's just one intersection point for cosine and x, and it's kind of right here-ish. And one thing I'll show you is that GeoGebra will actually find this intersection point for us, but use this sparingly, just to check answers. We still want to make sure that we are actually, employing Newton's method to do this. So if you do intersect and you select the curve and the line, we are given this intersection point, which GeoGebra approximates to be about 0.7390851,324, etc. Okay, so really there's Newton's method going on behind the scenes for GeoGebra to provide us with this particular number. So again, we're getting a sneak peek behind the scenes here to kind of see what's going on to be able to get this particular value. So I'm just going to hide that here. I'm going to hide this as well. And I'm going to hide this. So it looks like it called it f for me already, but I would like to use f later on. So let me just make this h instead, just so I can use f of x here. F of x equals cosine x minus x. So that was the function that we solved for. Sorry, it's still doing my intersect point there. This was the function that we are going to find the 0 for, cosine of x minus x. And notice that it equals 0. It looks like about the same thing, right? About 0.739, etc., etc. I'll just delete that duplicate one there. Okay, so first thing that we need to do is make an initial guess. Now, this is something that is kind of personal to you. You get to choose here what you want your first iteration to be. Just kind of, usually the choice is a whole number, but you could even do like 0.5 if you wanted to. I would say most people in this one would probably choose 1 as the starting point. But again, it really is your choice. So what we're going to do is I'm going to go ahead and do 1, all right? And we can tweak this around and kind of see which one gets us to the 6 decimal place accuracy faster. So there's our first one. Now what I can do is the same process as we did before. Equals, okay, now I need this value, x sub 1, minus f of x sub 1, divided by f prime, that's a g, f prime of x sub 1. Okay, enter. So this is our second approximation, is 0.75. And rather than typing that all in again, I can simply drag it down. And it looks like, okay, so we got 1 decimal place of accuracy here. And then between these two, we've got about, I guess, 4 decimal places of accuracy if you count the rounding of the 0.085. And then after that, from here to here, definitely both of these have accuracy within 6 decimal places. So this one has the first accuracy to 6 decimal places, 0.739085. And notice that that is consistent with kind of what we found in GeoGebra. But this, again, this piece should not be the way to find the answer, just kind of as an answer check. So I'm going to highlight that part there, and then don't need quite that much space. I'm going to print screen this piece. And feel free to go to here or here kind of up to you. And there's all the work that I did in Newton's method to find the root of the equation cosine x equals x, accurate to 6 decimal places. And if you get a GeoGebra account, you can actually sign up and you can save these applets for later use. So if you are working on your homework problems and you want to be able to go back and reference things, the work that you did to get the answer to that homework problem, you could even, section 4.7, number 5, whatever, and you can kind of keep track of all of those. All right, let's move on to some other explorations here. We're going to talk about some limitations to Newton's method, or just kind of cautions, things to be careful about. So Newton's method can fail for a few different reasons, and generally it has to do with that initial choice, that first approximation, that first x coordinate that you choose. So if you choose poorly, you can end up having Newton's method fail. So one example of that is if you choose x sub 1 to be at a horizontal tangent to the function. So notice, for example, in that that problem that we did with x cubed minus x squared minus 1, if you happen to choose x sub 1 to be 0, what you'd find then is that there's a horizontal tangent line there, and so it never crosses the x-axis. So Newton's method basically fails right from the beginning. You don't get a better estimate for the 0 of the function. And you can also see as well in the formula, the algebraic formula that we use, if there's a horizontal tangent, we have this issue of division by 0. So that's another issue. Now, even if it's not a 0 slope, but it's like a close to 0 slope, what can happen is that you can end up getting a worse approximation than your initial choice was. That is, the 0 of the linearization is even further away than your initial choice was. So for example, I'm coming back up to what we had done. Let's see. Let me look at it here. So if we had chosen like 0.5, for example, instead. So here, let's do this. If I change this to 0.5 as my initial guess, you can see that it kind of it eventually gets there, but it takes much, much longer to get there. It's like it takes the 12th approximation as opposed to it was like the 7th approximation with the other one. And the issue is that when I do 0.5, notice the tangent line has a negative slope, and it ends up making it go all the way over here to -4. And then we have to kind of do some catching up to get back over to where we wanted to go. It happens eventually, but it makes the process much slower. So that's why having a graph and choosing the right thing can be really helpful with these particular problems. Okay, so that's the idea of a near 0 slope. Okay. Some other issues that can come up but don't come up very often but are worth mentioning is the function could be non-differentiable at a particular point, like maybe at the 0 that you're trying to find. So like the cube root function, for example. If I pick something close by, and notice the x sub 0s and x sub 1s, but the process is still there, it'll kind of just continue to go away from that 0. Now, of course, we obviously know that the 0 of this function is at x equals 0, but think of a more complex variation of this, and it would be challenging to hone in on that particular 0 because of the function being non-differentiable at that point. You can also have domain restriction issues. So if you think about the square root function, again, this is an example where if I just pick the square root function, it's obvious that its 0 is at 0, but this is just a visual example. If I were to pick a point nearby and draw a tangent line, well, the issue is that the x sub 2 ends up being outside of the domain of the original function, so we wouldn't really be able to use Newton's method.